Welcome to this exploration of sound refraction. Sound is all around us, traveling through the air we breathe, the water in our oceans, and even through solid materials. But have you ever wondered what happens when sound waves move from one material to another? Today, we'll discover how sound waves bend and change direction as they travel through different media. This phenomenon is called refraction, and it plays a fascinating role in how we experience sound in our everyday lives. So what exactly is refraction? Refraction is the bending of sound waves when they pass from one medium to another. Imagine a sound wave traveling through air and then entering water. As it crosses this boundary, something interesting happens. The direction of wave propagation changes at the boundary between the two materials. This bending occurs due to a change in wave speed between the media. When sound enters a new medium, it travels at a different speed, causing the wave to bend. The angle at which the wave enters, called the angle of incidence, differs from the angle at which it continues traveling, known as the angle of refraction. But why does refraction actually happen? The answer lies in the speed of sound. In medium 1, sound travels at a certain speed, which we call v1. When the wave crosses into medium 2, it encounters a different speed, v2. If v1 does not equal v2, the wave bends. This speed difference causes the wavefront to change direction at the boundary between the two materials. Think of it like a car driving from pavement onto sand. One side of the car hits the sand first and slows down, causing the car to turn. Sound waves behave in a similar way when they encounter a new medium with a different speed. To understand refraction mathematically, we use something called Snell's law. The formula states that sine of theta 1 divided by sine of theta 2 equals v1 divided by v2. Let's break this down. Theta 1 is the angle of incidence, which is the angle the sound wave makes with the normal line in the first medium. Theta 2 is the angle of refraction in the second medium. v1 represents the speed of sound in the first medium, and v2 is the speed in the second medium. An important principle to remember is that when a wave enters a slower medium, it bends toward the normal line, which is an imaginary line perpendicular to the boundary. Sound travels at different speeds depending on the material it moves through. In air, sound travels at approximately 343 meters per second. That's about the length of 3.5 football fields in just 1 second. In water, sound moves much faster, at around 1,480 meters per second, which is more than 4 times faster than in air. In steel, sound is even more impressive, traveling at approximately 5,960 meters per second. There's a clear pattern here. Sound travels fastest in solids, slower in liquids, and slowest in gases. This happens because higher density and elasticity allow sound to propagate faster through the material. Temperature also plays a crucial role in sound refraction. The basic principle is simple. Warmer air allows sound to travel faster. On a normal day, we have warm air at ground level and cooler air above. This temperature gradient causes sound to bend upward, away from the ground. However, during a temperature inversion, the opposite occurs. Cool air sits at ground level while warmer air is above. In this situation, sound bends downward toward the ground. This phenomenon explains why sound travels farther at night. After sunset, the ground cools quickly, creating a temperature inversion that causes sound waves to curve back down toward the earth, allowing sound to travel much greater distances than during the day. Understanding sound refraction has many practical applications in the real world. In underwater acoustics, sonar systems must account for refraction in ocean layers to accurately detect objects beneath the surface. In noise control engineering, barriers are designed to redirect sound through refraction, protecting communities from unwanted noise. Concert halls are carefully designed to optimize acoustics using temperature and material properties, ensuring that every seat has excellent sound quality. Even in weather prediction, atmospheric refraction affects sound propagation patterns, helping meteorologists understand how conditions in the atmosphere influence the sounds we hear on the ground. Let's review the key concepts we've explored today. First, refraction occurs when sound waves change speed between different media, causing them to bend at the boundary. Second, Snell's law provides us with the mathematical relationship that describes this refraction process. Third, temperature gradients in the atmosphere cause sound to bend, which is why we can hear sounds traveling differently during day versus night. Finally, sound travels faster in denser, more elastic materials, which is why it moves quickest through solids and slowest through gases. Understanding refraction helps us control and predict sound behavior in countless practical applications, from designing better concert halls to improving underwater communication systems.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.